Oh, hello everyone. Sorry to be a little late. Let me share a presentation. Okay, hold on a second. Okay. I'm sure a lot of you are asking, where is your grade on test 3? And we are literally just a few tests on one problem away from solving any outstanding grading issues on our side. So it's unfortunately I have to make these decisions. So so I will be making them today, and then everything will be released. Okay. And last day to complete Zybook reading. So I just posted that after the exam week. So you have, you know, if you haven't read something from earlier part, of course, like prepare for test 4, right? Like read everything from chapter 10. You know, if you don't, you're just shooting yourself in the foot for the materials that you're tested on. But you know, previous stuff, just you know, if you don't have any finals, then just do it during the final week. If you have finals, focus on the finals and then finish the grading, the reading. I will take it on the Monday after the weekend, after the exam week. So that's in the email. And the list is there, it's posted. I mean, already some students went through the syllabus and basically put it all together. I will just make a list, link to where the student posted it. So just, you have to go through the syllabus, but one student already did that. So everything is clear in that post. Okay, and I'll just link to it. As usual with this Piazza, you know, is great, except if we have like 5 different conversations on the same topic, then somebody has to cross-link all of this. Yes, and I'll put that also a link to that post from this website, so it's in one spot. If I put it in many places, then the problem is that if I make a mistake in one of them, then it's even worse. So it's better if it's in one place, and then everything links to that. All right. Okay. All right. Okay. So I guess that's logistics, and maybe let's save some other logistics to the end. Oh yes, and grade scope homework 9. Sure. Yes. Yes. I mean, okay. I'll do that after class. All right. Okay, I think that's it for your questions that I see here. Okay. So let me try to go through a bunch of these additional counting problems and different counting problem types. So here is one. We did sequences with repetitions last time, like Mississippi, which has, you know, 4 S's and okay, I forget how many. It's a complicated word. So this is a sequence, and the question is how to permute this. So these are permutations, in other words, sequences, ordered objects, but with repetitions, because you have a certain budget for I's, certain budget for P's, certain budget for M's. How about a set? But what is it? So a same type of thing, but unordered. Okay, but what is that? Because a set with repeated elements is not a set. You know, for as far as set is concerned, we always said that, right? Like that, adding the same element to the same set, it makes no difference. Okay, so here is, you know, the repeat of where we are. I'm not going to go over this. This is, you know, just a snapshot. And so we unordered sets with no repeat, which is normal sets. We know how to count. It's n choose t. where n is element in the set and t is the how many elements the subset has to have. So what about unordered objects with repeats? Well, first we have to define these are not sets. These are something called multiset. It's like a set, but with certain rules for repeats. So let's say, so a multiset is unordered data structure that you can have multiple copies of the same thing, but it's unordered. Okay, so for example, here is a list. Because the order doesn't matter, so I can introduce some canonical order to represent these. And if these are different objects, then there is always going to be some canonical order, like lexicographic order. So like encode them somehow, and then just lexicographically order them. If you just lexicographic order is nothing but map it to bit strings, and then just order bit strings in a normal greater or equal over, right? So because bit strings are just representation of integers in the end, right? So anything can be ordered in some natural order, lexicographic, and here is just integers, these objects, so I can order them in an obvious way. But this is just for representation purposes, so I don't get confused about like two objects of this type that are the same and they're just represented in a chaotic way, so I cannot tell that they're the same. So it's a list where the order doesn't matter, but 2 occurs three times and 7 occurs twice. And I'm going to call this a different, all these lists, they are going to be different from my point of view. Okay, so you can imagine in computer science that this would, occur. Like there is some data structure where you might have multiple occurrences of the same thing, but you don't care about the ordering. The number, like, you keep track of the students who did bonus exercises, and you want to make sure that if a student did bonus exercises on 2 different sets, the student occurs twice on the list. But you don't care about the ordering of the students. This is the list of students who did bonus exercises. So if somebody occurs with multiplicity 1, it means that they did it only on one, got a 1 bonus problem. And if they occur with multiplicity, higher than 1, that's the number of bonus problems that they've done. Okay. So if I thought of this as ordered, then these 2 sequences are different, but they're made of the same elements. So if I if I remove the order, they all represent to the same multiset. They all correspond, to the same multiset. So here's an example of this kind of counting problem. You're purchasing 12 donuts, and there is 4 donut types: chocolate, glazed, jelly, maple. And I'm sorry if some of them, don't sound good to you. So for this, okay, and there is unlimited supply of each variety. And the question is, how many donut bags can you get, right? So you're getting 12 donuts for you and your, student club, a small club, I guess. And the bag might contain, all chocolate or all glazed, or half chocolate, half glazed, or 3 of each. 3 chocolate, 3 glazed, 3 jelly, 3 maple, right? All of these are different choices, but every chocolate donut is identical. So I don't, if there is 100 chocolate donuts in the donut shop, I don't care which of these 100 you picked. All I care is that you picked a certain number of chocolate donuts. I also don't care how did you place them in the bag? Did you put all the chocolate on top or on the bottom? I don't care. So it's a multiset. It's unordered internally. and it's made of certain multiplicities of identical objects, of objects that I treat every chocolate donut I like as if it's indistinguishable. So here is a sample selection of 3 chocolate, 1 glazed, 6 jellies, and 2 maples. And because I don't want to be confused about selections being identical, so I'm going to create a certain representation, which I will put all the C's in front, then G's, J's, then M's, alphabetic order, okay? And this is arbitrary. This is like my decision for how to represent them, but it's natural because it's alphabetical, okay? So, and now note, okay, so like how do you represent all chocolate? Okay, these are all C's, right? And half chocolate, half glazed. There's 6 C's and 6 G's, right? So every selection can be represented in this way. Okay, how do you count them? Well, I'm going to argue that you can count them by just setting boundaries between these 4 regions. So each selection corresponds to certain choice of the boundary where C's end. They always start with C's and it always ends with M's. If you don't have any C's, the C boundary is still there. It's just going to be at the very beginning, right? So a selection with all M's would correspond to setting the CG boundary, GJ boundary, and JM boundary all right at the beginning. So every place, so I have 3 boundaries to choose. Every choice of these 3 boundaries gives me a choice of a different donut bag. And right, and also every donut bag has a unique representation in terms of setting these 3 boundaries as some indices between the beginning and the end. So that's the key to counting multisets. And there might be other way to count, but there would be awfully, I bet you that any other way you're trying to count, you would come up with some, complicated formula. It would exist, I'm sure. There's other ways, right? But they're just going to be more complex. And they better be equal in the end, but it might be not so easy to see that these 2 ways of counting are equal. So if all I'm setting is the 3 boundaries, then therefore, basically, I'm setting 3 bits equal 1 somewhere in the bit string. And the indexes where I'm placing the ones are going to be defining these boundary conditions, these boundary places. So every selection corresponds to a bit string that contains exactly 3 ones in certain indices, because that defines 3 boundaries between, chocolate and J, whatever that was, G and J, and then M. I'm already forgetting whether G or J comes first in the English alphabet. The question is, okay, how long? You have to be careful. How long are these binary strings that represent them? If there is 12 donuts, is the bit string that represents these boundaries of length 12? Not exactly. So I spread them out so that to allow place for the boundaries, and I represent in this way. The zeros would, in this encoding, you can read it in the following way. This bit string is an encoding for how to make a choice of the donut bag. The encoding should be processed like this. If you encounter when you start, your first flavor is C, because that's the lowest letter of alphabet. Okay, you have 4 letters and they're ordered C, G, J, M. At the beginning, your flavor is C. If you see a 0, add the C character to the choice, to the multiset. And just recurse. If the next bit is 0, add the current letter to the multiset. If you see, and just do it going from left to right in the string. If you see a 1, switch from the current character, which is the lowest, right, C, to the next one, which is G. And just recurse. So your variable in this encoding is the current letter. Ordering on the letters is the parameters that is you have to keep in the back of your head. And then you do so your current variable is you start with a C, and then if you see a 0, add the current variable to the multiset. If you see a 1, switch to the next variable. So your variable becomes the next letter in the ordering of between these characters, C, G, J, and M. And that's it. That's the code that interprets the string and creates a choice of 12 donuts. And look, convince yourself that every bit string like this, if there is any single bit that differs in this bit string, then it actually will correspond to a different choice, right? Because if there is any difference, so that means that these ones are in, one of these ones is in a different position. That will mean that the length of these regions must have changed in at least one region. And therefore, that would represent two different multiplicities of these letters. The other direction, okay, so it's fine. So every 2-bit strings create different donut bags. So there's no collisions in it. It's a one-to-one function from bit strings to donut bags. But is it onto? Is every donut bag covered by some bit string? Yes, because it's obvious that there exists the inverse encoding, right? I can, in fact, this is what is shown here. Whatever donut bag I have, I make these splits. I shift the different donut flavors so that to make places for ones, and I put zeros for my donuts, and I put ones in those gaps. So these encodings exist. So therefore it's onto. So therefore it's a bijection. So therefore all I need to count how many of these I have is I have to count these substrings. How many strings like this exist? And that's easy. It's all the strings of length 15, 12 for the zeros, and 3 for the ones, then have exactly 3 ones. So it's, okay, sorry. So it's 15 choose 3, right? It's the number of bit strings of length 15 with exactly 3 ones. Okay, so okay, so here is one encoding. Here is like, what if I had no M's and no T's? Well, my boundary would be right after another. So my little program would say, switch to the next letter, and actually switch to the letter after. Never use that one, right? Because there was no 0 in the state. Likewise, at the end, switch, but don't use, right? Because there is no 0 afterward. So that would be encoding. And let's say I have all the G's only, right? So I switch at the very beginning. Then I have 12 zeros, and then switch and switch at the end. Okay, do nothing with that. So it's the number of donuts is the 12 here, and the number of switches, context switches between two donut characters is the number of flavors minus 1, because I start with the first one, and so the number of switches is types minus 1, number of types minus 1. Okay, so here is my encodings, right? You can verify this. I mean, how to read these encodings and translate them into donut bags. And so therefore the final answer, how many to count, is a number of 15-bit strings with exactly 3 ones for these character switches that encode character switches, encode flavor switches or type switches in the selection of elements into the multiset. So in this case, if I have 12 donuts and 4 varieties, I add 12 to 4 minus 1 for these type boundaries. So that gives me a bit string of length 15, and I have type minus 1 of boundaries designated by ones, so it's 15 choose 3. In general, you have n items and m varieties. So the counting asks how many multisets are there that have n total elements, and the elements come from m types. In the previous example, there was 10 elements I wanted to choose, 12 donuts, and the number of varieties was 4, m was equal to 4. But this is a general thing. If your alphabet contains m characters, and you need to take a multiset of length n, this will be the formula. It's n plus 1 minus the varieties, because this is the length of the bit strings that encodes this choice. Choose m minus 1. This is the number of boundaries between the types, or type switches in my little code that creates these multisets from their encodings. And here we assume that the length of the multiset is larger than the number of characters in our example, but we don't have to assume that. In fact, if the number of these characters is greater, it still works. Okay, you will have just more ones for contact switches, and because if the number of ones is greater than the number of zeros, then of course there are going to be no zeros between some ones, but that's okay, because there were apparently too many types, and you chose a much smaller selection, right? Like you go to a donut store and there's like, I don't know, 30 flavors or something, right? And hopefully you're buying less than that. So, okay, so, some other examples, right? Like in the same vein, 75 varieties of taffy, but you only choose 12 out of these 75 possibilities, right? So that's a case where the number of varieties, m, is going to be much larger than the number of the size of the multiset you're choosing, which is the n, but it's okay, right? It's a bit string of this length. So just remember that the number of types you have to subtract 1 if you want to use this encoding, because the encoding is about boundaries between types. So if you have m types, you have m minus 1 boundaries, or m minus 1 of these ones that encode those boundaries, right? So it will be a string of 86 with, well, 74 ones, but equivalently, of course, you can just count zeros. So you can do 86 choose 12, but that's because of this general formula, right? That some value choose m minus 1 is also can be represented as that value choose the difference between that value and m minus 1, which is n, right? So if you have to compute it numerically, then you would just choose the smaller here of the two, but you know that they are equivalent anyway, right? As a reminder to everybody who is, if somebody was not paying attention before, we will not ask you to evaluate any of this numerically. In fact, for many reasons, it's much more preferable if you don't. Safer for you, easier for us. If you make any counting mistake, having the formula at least allows us to see where did you make it. Perhaps your mistake was trivial, I don't know, you thought you were counting only lowercase letters, in which case there's 26, or both lower and upper, in which case there's 52, and we can understand that if you give us a formula, and we can understand nothing if you give us the full evaluation, numerical evaluation of this thing. So, okay, another example. There's 4 computer types. A cluster consists of 25 computers. Okay, soon these things will be completely obsolete. Everybody just carries their own computing equipment somewhere. But for those old enough to remember computer clusters, that's a relevant question. So how many cluster types there are, right? I can form a cluster type by choosing the 25 computers from different types, right? And the only computer type, and the only thing that matters is the multiplicity of each of the types. This is exactly 25 donuts that I have to choose from 4 flavors, right? Because you're told that the only thing about a cluster that matters is the number of computers within a given type. Okay, so it's 25 plus 3, right? Because the number of types minus 1, choose 3. Again, number of types minus 1. Okay. Okay. Here is a paradigm for how to think of these many choice questions that captures a lot of stuff that we've been talking about in a sort of a framework, like a universal framework, if you will. And it boils into bins. So you have a bunch of bins and a bunch of balls, and you're throwing the balls into bins, and your selection of toys for kids, or prizes for students, or computers in a cluster can be represented as how many balls fell into which bin. And the whole thing will be about, are there constraints? Perhaps one bin cannot take too many balls. Are the balls different? Are they like labeled? And therefore it matters whether balls of different type index fell into the same bin, or the only thing you care is the multiplicity of the balls within a certain bin. And every problem we've talked about can be mapped into this language. Okay, so how many? So here is one counting problem. Let's say that all the balls are identical, but so there's no difference between the first ball, second ball. You just have n balls. They're all gray, and you're putting them into bins. And there is a constraint that every bin either can take a ball or not, but once it takes a ball, it cannot take more. So now the bins are always distinguishable. They go from first to number m, now what happens if the balls are not all the same? They're actually different. They are labeled 1, 2, 3, all the way to n. So it doesn't, it's not only that a certain bin was filled with something or not. It also matters whether it was filled with ball number 1 or ball number 7. But you have the same constraint. Okay, now, sorry. Okay, so these two we know, right? Because this first counting problem is, well, the balls are basically choosing the bins because of this constraint. If I have n balls, then I have to choose n of the bins. So I'm just choosing n bins out of m total. So it's m choose n. And indeed, it can be only done if n is smaller or equal, right? Indeed, with this constraint, if I have too many more balls than bins, I cannot do it. There is no such assignment, right? And in the extreme case when they are equal, there is only one choice, just occupy all bins. What if they are ordered though? So what if the balls are labeled? It's choosing an n permutation of the m element set. So you can think of the numbered balls as creating a sequence between the bins. The first bin would be the one where the ball number 1 fell. That chooses the first bin. And how many choices I have? M. The second ball will tell me what's the second bin. The third, what's the third bin, and so forth. So the choice of the distinguishable balls, how many placings I have, is the same as choosing n, the number of balls, out of the m, the number of bins, and then ordering them. You can see it also here, right? I chose a set, and then I have to stop pretending that all the balls are gray and give the ordering to the balls. How many I have? I have to take this and multiply it by n factorial. That gives me this. It is not immediate that the choice of these bins by balls which have indices can be represented as an n permutation of the bins. But it's not that hard to see either, right? But it's not like an immediate connection. What if I don't have the restrictions? Okay, so I'm putting these, but my balls are still different. I don't have the, I remove this restriction that the number of balls has to be either 0 or 1. So if the ball number 1, the ball number 2, the ball number 3 are just telling me which of the bin I should take first, which of the bin I should take second, which of the bin I should take third, then this problem is a problem of taking an ordered sequence of bins of length n with no repeats. Because if I took a bin, I cannot take it again, because that means throwing another ball into the same bin. But if I remove this constraint, that simply means I can, it's again, order, a sequence of bins of length n, and but now I don't have the constraint. I can take the same bin again and again. So that's actually super simple problem. It's just a number of sequences of length n made of the alphabet of length m, right? Because for every ball, or other ways, okay, look, how many choices every ball makes? M. Is there any constraint on the next ball because of what this first ball did? No. Every ball has m choices. So obviously it's m to the n. And here I can also represent, so maybe this whole parallel with sequences is unnecessary and not natural. Much easier one. Every ball takes, the first ball makes m choices, the second m-1, because it can only fall into an unoccupied bin. The next choice is m-2, etc. That's exactly this formula, right? What about this? I remove the constraints, but my balls are all gray. Yeah, so what do I do, right? So like now, and it's too bad that, okay, somebody say, oh, wait 30 seconds. What is this? this thing was a set. I was choosing an n element set, subset, right, from a set. And this, yes, it's a multiset. It's a multiset. Thanks, thanks, Matthew. It's a multiset, right? Because what am I choosing here? I have to choose. I have these n balls, so they're going to choose bins, but some of the bins can be done with more multiplicity, right? The balls tell me which of the bins you choose and with what multiplicity. And the total number is n, because I have n balls. So it's a multiset. This thing is a multiset of size n made of characters in an alphabet of size m. So this is the formula. This is just what we did. Okay. And this is an unordered selection with no repeats, right? Because it's unordered because the balls are gray, are identical. Here is the ordered with no repeats. Here is the and here are the repeats allowed for the ordered, which is the easiest, the first thing that we started with. And the unordered with repeats that remain a mystery until now. This place in the quadrant of choices. So here is the explanation for the multiset, right, which I sketched. Throwing balls, identical balls into these bins is just a multiplicity of bin 1, multiplicity of bin 2, etc., where the total number of elements is the number of the balls, right? So, okay, some examples. How many ways to count? You have 10 prizes to give to 200 students. And you don't have a constraint. You can give the same students the same prize. Okay, so it's 200 choices for every 10, and these are independent choices. Okay, I don't. Yeah, sorry, I might. Hold on. Oh, right. But I got confused here. These were identical prices. Sorry, in my example. So, so this is it's a strange case where I can give the same. Even though my prices are identical, I can give this different amounts to the same student. Think of that as like the number of bonus exercises the students made, right? And okay, although that's unnatural because like why would there be a limit? Okay, so these are prizes, and but somehow I can give many to the same person. So these are identical balls that fall into 200 bins, and so it's a multi-set made of 200 characters out of the alphabet of 200, but the length of the string from that alphabet, length of the, okay, it's not a string, it's a multi-set, contains 10 elements. So it's 10 plus 200 minus 1, choose 200 minus 1, or equivalently 209, choose 10, right? Rather than, I could put 199 here, but putting 10 is an equivalent, right? Because 209 minus 199 is 10.
So why is it that n minus 1 is the same as n?
Because they sum to 209. Yes, because of this, because n minus 1 and n sum to this. So that's why n choose A is the same as n choose B, as long as A plus B is n. Right, so this is the case of the general formula.
Right, so you're saying you can always replace n with m minus 1?
In this case, where my the stuff that I'm choosing from is n plus n minus 1.
Right.
Right. Okay. So if I have a limit of a price per price per student, then this becomes not a multi-set but a set. So the number of choices is just 200 choose 10. And what if the prices were different? Okay, with the same constraint, then it would be an 10 permutation of a 200 element set. Okay, so this. And what if I didn't have, the prices were different and I didn't have a constraint? Then it's just a string of length n out of the alphabet of 200, because each of the n choices is independent now. So it's 200 to the 10. All right. So the different notions of, is the price the same or not? And is there a limit on the prices or not? Basically create a different place on the spectrum. Okay. Oh yeah, somebody wrote the correcting. Okay, except of the capital letters on the chat. Okay. Here is a surprising application, perhaps, is that okay, how many solutions to an equation like this over integers where the variable is limited to non-negative integer? So how many assignments of x1, x2, x3, x4 there are to sum up to 12? Actually, so every assignment is a sequence of integers. Each of them is non-negative, and they have to sum to 12. This is exactly the multi-set question. I have 12 balls and I need to place them in 4 regions. Either making, I have 12 because they have to sum to 12. If I place 2 balls in the x1 region, that means that x1 is 2. If I place 4 balls in the x2 region, that means x2 is 4. So this is exactly the multi-set problem, where the multi-set is my types are these variables, and the number of donuts or the size of the multi-set I create is 12. So it's a multi-set of size 12 with 4 categories, with 4 types. So it's a 12 plus number of types minus 1. So number of types minus 1 is 3. So it's therefore it's 12 plus 3. Choose 3. It's a multi-set formula. Okay. Let's say I introduce a lower bound. So I say, okay, you have 12 donuts from 4 varieties, but you have to have at least 12 of, let's say, chocolate. How do you count now? Easy. Satisfy this bound. So place 12 donuts, 12 balls into the bin for the chocolate. Because you have no choice, you have to place 2 there to satisfy this constraint. After you satisfy this constraint, use the remaining 10 balls in any way you want. In other words, some can fall still into the chocolate bin. They can fall into other bins. You can convince yourself that a placement of balls that has in these 2 phases will create every placement that satisfies this requirement. And moreover, it will not create any 2 of them, so they will not collide. You cannot recreate the same assignment using 2 different runs through this algorithm, through this process and this process, right? So the number is just, you reduce the problem to choose fewer donuts placed without restrictions. So it's again multi-set, but with just reduced number of donuts, right? So it's now 10 donuts with 4 types. So it's 10 plus 3, choose 3, like here, right? In other words, introduction of this bound it just shifted the problem. It reduced the freedom by having to take 2 balls and place them in this one bin, and the rest of the balls were unconstrained. So therefore, it's the same multiset problem, just with reduced number of balls. Okay. There's some questions on the chat as if I made some typo here. Why isn't it 9? Yeah, it's not 9 because in order to satisfy this at least 2, I satisfy it by, relinquishing freedom on the 2 balls. I place them in the chocolate bin. After that, I have complete freedom with the remaining 10. So I still think this is a problem, multiset problem of 10 balls with 4 bins, which is this formula. Okay, and now if I didn't have the constraint, right, I will just have 2 more balls, so it will be this. Okay. If you evaluate them numerically, this is, roughly like 14 times 15 higher than this, right? So, removing this freedom drastically removes number of choices. You can also map this into these numerical problems. Let's say that I have this formula, and but now I have constraints. Let's say x2 is not only non-negative, but actually greater to 1 or equal, and x4 has to be equal, greater or equal to 3. Well, so that's exactly the same thing, right? I waste 1 ball to satisfy this constraint. I waste 3 balls to satisfy this, and the rest, 12 minus 1 minus 3, which is 8, can be placed anywhere. Okay, so it again reduces to the balls into bins placement with the identical balls, but now it's a multiset of size 8 out of alphabet with 4 characters. So it's 8 plus 3, which is 11. Choose 3. Okay. What if I told you that, well, okay, or like, this is 12 identical balls into 4 bins, and I have to have at least 2 in each bin, then I just waste 8 right balls, because it's 2 times the number of bins, and I have only 4 balls that are free, right? So it's the same multiset formula, but with just 4. The multiset is of size 4 now. So kids into chocolates. I mean, sorry, chocolates divided between kids. If the chocolates are identical and each kid has to get at least 1, you waste 5 of the chocolates to give equally, and then you have 10 remaining balls with freedom, right? So it's 14 choose 4, right? Because this is a multiset with 10 elements with 10 size of 5 types. So it's a 10 plus 4, choose 4. Here is counting by complement example. How many, if you introduce a constraint like this, it's an upper bound rather than a lower bound. So let's say that in a store, some selection, possibly many selection, but let's say 1, there's only 5 chocolate left. So any selection you make can have at most 5 chocolate ones. Well, I can count it using a complement, counting by complement rule, right? Like this. Any selection that satisfies this constraint, the set of selections that satisfy this constraint is the set of all selections minus the set of selections which violates this constraint. Okay. Now, what does it mean that the selection violates it? It means that it's a selection that has not smaller or equal to 5 of chocolates, right? So it is actually a selection that has at least 6 chocolate. And that we know how to count, right? Because you have 12 donuts into 4 varieties. So you waste 6 donuts to satisfy this constraint. You have 6 donuts left. So it is, and how many flavors you have? How many boundaries you have? You have 5 types. No, sorry. You have 4 varieties. 4 varieties, 4 types. So 12 plus 4 minus 1, choose 4 minus 1. Sorry. Okay. Yeah, I made a mistake and now I'm making more mistakes. Okay. We were here counting this. I'm saying this. You can count this and you can count that. Counting this is the standard 12 choose 12 multi-set of size 12 with 4 varieties. So it's 12 plus 4 minus 1, choose 4 minus 1. That's this box. And I have to remove how many choices violate the constraint I want, right? And that's the number of choices of 12 donuts among 4 varieties, which satisfies this lower bound constraint. But that I knew how to count from previous slide. I waste 6, and after that I have 6 free. 3 donuts, I have 6 free donuts to choose, that I can choose any flavor. So it's 6 plus 4 minus 1, choose 4 minus 1. Okay. So the lesson here, lower bounds are easy. You just waste some balls to satisfy the lower bounds. And after that, you have freedom, so it reduces to the multisets problem, with just reduced number of balls. Upper bounds are again easy if you think by counting by complement. So translate an upper bound into everyone except those that do not satisfy the bound, upper bound. So they're not smaller or equal to something, and therefore they are greater or equal to something else. But you have to be careful because there is a switch. To violate 5 chocolate or less, I have to have 6 chocolate or more. Okay, so these are easy mistakes to make if you are in a hurry, but still, that's unfortunate. But yes, and like I just made a mistake by thinking that these are the types, the number of types. No, these are the number of types. So that's again something that you have to try to be careful when you answer these. Don't get confused. What was the bound constraint? What was the number of objects used? Types. Okay. Okay. So, okay, just another case. I have 75 varieties of taffy, and I choose 12, but a certain variety has only 7 left, right? So again, this is the number of choices is the unconstrained choices. I select 12 from 75 types. So a multi-set of size 12 of characters that are of 75 characters. But I subtract all those who violate this constraint, which is those that have at least 8 strawberry flavor, right? So this one, I take how many I have left. I waste 8 from the total budget into the strawberry flavor, and I have 4 remaining. So it's 4 plus number of boundaries, which is 75 minus 1. Choose 75 minus 1. And this guy is 12 plus 75 minus 1. Choose 75 minus 1. Okay. Okay. How many? Oh my goodness. Okay. I'm way over time. I didn't notice. I believe I have one more counting problem on these slides, but okay. I'm out of time, so I will ask you to look at these on your own. Okay, now we'll take questions if you have them.
Professor?
Yes.
When we're discussing the at least amount, so if you go back like 3 slides to your first at least question, one more back, I think one more.
Which each kid gets at least this one?
No, that's at most, so...
Okay,
I mean, sorry,
at least. Okay, so
yeah.
let's say this one.
Yeah, so there was I think there was one with 2 chocolate donuts. I think it was before this one, lower bound, yeah. Yeah, this one. So can you just discuss why we don't take into account these 2 chocolate donuts whatsoever? Because it seems like we're just pulling them out of the subset, and then we're counting.
Yes, right. Well, because here's the intuitive thing. Like, if you're told that you have to have at least 2 chocolate donuts, then the first things you're gonna go, like, if your buddies tell you, okay, get a bag of 12 donuts, but at least 2 chocolates. So what you're gonna do in the store? You just get 2 chocolates. That's the first thing you do. Okay. And then what's your budget? 10. And do you have any constraints with these remaining 10? You don't.
Okay, I see.
Right. So that's it.
All right, perfect. Thank you.
Thank you.
Could you explain one more time when m-1 is equal to n in the multi-set combination?
You know what? It's like, because n and m is hard, so I will just write it as a formula. N C choose. Okay, C choose A is A to C is the same as A choose B if B plus C equals A. Okay, so that's what I wrote on the tab.
Okay.
And here, if A equals n plus m minus 1 and C equals m minus 1, then this works for B equals n. Yeah, the n and m are hard, and right, so therefore treat n choose
okay, yeah, that makes much more sense. Thank you so much.
okay. Yeah.
Do you know when you'll be posting these slides?
I'll be posting them straight away. Oh, sorry for not posting them. I usually give them to you at the beginning of the lecture, but I forgot.
No worries.
Yeah.
Can you go over the remaining example in your slides?
Which one?
The very last example that you said we don't have time to.
You know what? I mean, I'm not so sure. Okay, yeah, sure. So whoever is still around, I'll have to go off in 5 minutes, but I will see what I can do. Okay. So you know what? Basically, I'm trying to. You know what? Sorry, this is a horrible animation here. So something is messed up with my slide here. Sure. Okay. Oh, hold on. I will share the screen. Okay. Okay, do you guys see this the presentation?
Yeah.
Okay. Okay. So no, maybe I can do that. Okay. So here is a way to divide the spectrum of choices in yet another way. Okay. I have the following constraints. I mean, spectrum of choices. So these are all balls into bins, but I can make balls all gray, or I can label them. I can have a constraint that there is one per bin, or I have no constraints. And also I can have constraints as in like in the middle, which is that perhaps I have a constraint same number per of balls per bin. So if they are indistinguishable, the balls are indistinguishable, and then I'm just choosing you know, as so you have 3 balls and 5 bins. I'm choosing 3 bins, and it's a set. So this part is just M choose N. Okay. What if I make them distinguishable? Okay. So this is like as if the balls are labeled. So it's like a choice of the bins plus ordering between them. So it's 5 choose 3 plus the ordering times the ordering. Sorry. So it's a 3 permutation out of a 5 element set. So this is the box. This box is number of n permutations of an m element set. Right? I choose n bins and I permute them, and the order matters. Now, let's see if I have no limit on the number of balls per bin, and the bins are all the balls are all and the balls are all labeled. So you know, I don't have the best colors, but these 3 are of the different color. So this is just throwing the ball. Each ball is independent. I have 3 of them, 5 bins, so it's 5 to the 3. And in general, if I have basically this corresponds to independent choices of the bins, so it's this. What if the balls are all gray? So we already went over this. This is the multi-set, 3 elements from a 5 character set. But the characters may take certain multiplicity, right? Not just one. So it's a multiset. So if the multiset is of size 3, and I have 5 types, then it's 3 plus 5 minus 1. Choose 5 minus 1, and the general formula for a multiset is this one. Now, what about these? If I have the same number. So let's look at this one first. I have distinguishable balls. Okay, so first of all, this is the only way to satisfy this if M is some multiple of N. So if the total number is M and I have N bins, then I place M divided by N into every bin, right? So here, if I have 10 balls and 5 bins, I have to place 2 into every bin. So this is like permuting the balls, and then ignoring the permutations within the bin. So it's 10 factorial divided by 2 factorial for ignoring these, 2 factorials for ignoring these. So this is the formula this is what we had last time. I am ordering my balls, right, completely, and I'm throwing them into the bins. The first, whichever ball, n over m balls I chose first, fall into the first bin. Whichever n over m balls I first chose second, the next segment falls into the second bin, etc. But within the bin, the permutations don't matter, so I have to remove them. So that's another version of the Mississippi problem. It is not immediate like that these two counting problems are equivalent, but they are. Okay, it's the Mississippi in some way is connected with the can be represented as throwing balls into bins, and with that I have to throw certain number of balls into first bin, I have to throw certain number of balls into the second, etc. The balls were positions within a string, first, second, all the way to, Mississippi has, I don't know how many characters it has, let's say it has 11. So there's 11 positions, and I have to throw one position into M's because there's only one M in the word Mississippi. I have to throw 4 positions into I's because there is 4 I's in Mississippi, etc. So that's how you can think of permuting letters in the Mississippi as a case of the ball into bin problem. And if you have a simplified constraint that simply all of them have to be equal multiplicity, then you have this formula. If you have certain multiplicities for bin 1, certain for bin 2, etc., and they're all fixed, all you do here, you multiply the multiplicity constraint factorial times multiplicity constraint on the second bin factorial, etc. Okay, but if all of these balls are now indistinguishable, then there's only one choice, right? Because you fill them in the prescribed way, and there is no choices. Okay, so this is the full workout of working out of this table. And I have extra material about inclusion exclusion, but I knew that I wouldn't get to it, so I'm removing it from the final from test 4. And I said that like a few days ago, that basically we will only get to I will not have this on the, so it will be on the slides. You are required to read. It's part of the reading, but it will not be on test 4.
Thank you so much.
Okay, you're very much welcome. So I will stop recording now and see you Wednesday.